Good afternoon, Advanced Algebra students. I hope you are doing fantastic. I am looking forward to starting Chapter 6 with you. We just finished Chapter 5, where we learned about rational exponents. So we talked about their properties, simplifying expressions with rational exponents, and solving equations with rational exponents. We're going to build on that in Chapter 6 by looking at key features of exponential functions, developing exponential models, and evaluating inverses of exponential functions. So one of the first things I'd like to do is to identify some key features of exponential functions. We do have either exponential growth or exponential decay. So let's go ahead and put the title of our notes here is going to be 6.1, Key Features of Exponential Functions. And then for example 1, we're going to look at f of x equals 2 to the power of x. So what we typically do when we're graphing something like this is just graph a couple key points. Usually x is 0 and x is 1. The reason is because if we're putting in 0 for x, 2 to the power of 0 is 1, and 2 to the power of 1 is just 2. I'm going to adjust the camera here so we can see just a little bit more of the board. There we go. And then we want to just graph those points. So we're going to graph the point 0, 1 and also 1, 2. Now, those obviously are just 2 points, but the basic shape of an exponential function is going to look like this. So what do we notice about the key features of this function? Okay, in terms of the domain, we can see that the domain is all real numbers. In terms of the range, we can see that y is always going to be positive. And then there's an asymptote here, and that is y equals 0 or the x-axis. And then what we can say if we want to describe this more formally is as x approaches negative infinity, in other words, as we go to the left, y approaches 0. So we can see that y is getting closer and closer to 0, but not actually touching. And as we go to the right, or as x approaches positive infinity, y approaches positive infinity. That means it gets higher and higher. So this would be exponential growth. And the reason why we would know that it is exponential growth is because this number here is greater than 1. So it's going to be growth. The number being raised to the power is greater than 1. Let's look at an example of exponential decay. So f of x equals 5 times 1/2 raised to the power of x. Because this number here is x, we'll call this b, is less than 1 and greater than 0, this is going to be exponential decay. Again, we can get away with just plotting a couple x values, so let's look at 0 and 1. If x is 0, 1/2 to the 0 is 1 times 5 is 1. 1/2 to the power of 1 is just 1/2, and half of 5 is 2.5 or 5/2, whichever you prefer. Now, when we graph this function, we're going to go 0 over and 5 up, and then 1 over and 2.5 up. This function is also going to approach the x-axis as an asymptote. So let's look at the features here. Again, the domain is all real numbers. The range is also y is greater than 0. Y cannot actually equal 0. The asymptote here is the x-axis. And then again, we can describe the ends of the function by saying as x approaches negative infinity, y approaches infinity. That means as we go to the left, y gets greater and greater. And then as we go to the right, or as x approaches positive infinity, then y is going to get closer to 0. Y approaches 0. Now, we can also graph transformations of functions. So we can shift these functions. So let's say, for example, we wanted to, for example 3, we wanted to look at g of x is equal to -3 to the power of x. So this is going to be similar to the first example we did, but the fact there's a minus sign here is going to do what? This minus sign is going to flip the fraction, or excuse me, the function over the x-axis. So if I want to do a little plot here for x values of 0 and 1, when x is 0, then y is going to be -1. When x is 1, then y is going to be -3. So we want to see, and I guess on this particular question, the question was, how does this compare to the graph? Compare to f of x equals +3 to the x. If I was going to do a little t-chart for +3 to the x, when I plug in 0, I would get +1, and when I plug in 1, I would get +3. So this parent function that goes through 0, 1, and 1, 3 is going to look like this. However, if I put this minus sign here and graph it, I'm going to be going through the point 0, -1, and 1, -3. It's going to be flipping the graph over the x-axis. So what we would say is that this would be reflected across the x-axis, and the asymptote would be the same. The asymptote is the same as this other function. Our intercept here, our y-intercept on the parent function, the y-intercept is 0, 1. Here, the y-intercept is 0, -1. All right, I do want to go over 2 basic growth and decay functions. So they are often used to calculate numbers with financial matters or population. So let's talk about those. With exponential growth, most of our exponential growth functions can be written in the form y equals a times 1 plus r to the power of t. And for decay, we would write it as, let me make a little more room, y equals a times 1 minus r to the power of t. With both of these functions, if we're calculating problems using financial matters or whatever, this A represents our initial amount. So it could be, for example, an initial investment. And then the R is the rate of increase or decrease. So it's our rate. And the T is the time in years. Let's do a specific example. Oh, and then 1 plus R, this is the growth factor, and here 1 minus r would be the decay factor. So let's do an example where we determine whether a function represents exponential growth or decay, and then we're going to write the base in terms of the rate of growth or decay, identify r, and interpret the rate of growth or decay. So let's say we have y equals 220 times 1.05 to the x. We can think of this as, if we want, as y equals 220 times 1 plus 0.05 to the x. So this would be our growth factor. If we're just interpreting this function here, r, which is our rate, would be equal to 0.05. And that means that the rate of growth would be 5%, because 0.05 in percent form is 5%. All right, let's do another example. Let's say that we have y equals 24 times 0.8 to the x. We can think of this as 24 times 1 minus 0.2 to the x. So this would be a decay factor here because we're subtracting from 1. R, which is our rate, would be 0.2. And that means that the rate of decay would be 20%. Okay, let's do, I think probably one other example is good. I might do two. We'll have to see how long this one takes. Let's do a real life application problem. So let's say that the population of a large city, and by the way, you don't have to write all the words down, just what I put on the board. But the population of a large city was about 4.6 million in the year 2015 and grew at a rate of 1.3% for the next 5 years. Write an exponential function to model the situation and use it to approximate the population in the year 2020. Round to the nearest tenth in millions. Okay, so it's telling us the initial amount or the initial population. I think this is our 5th example here. Our initial population was 4.6 million. So I'm just going to write 4.6 in millions. It says it grew at a rate of 1.3%. 1.3% in decimal form is 0.013. And then it says that it grew that way for the next 5 years. So if I wanted to write a function to model the situation, I could simplify this by putting 1.013 in parentheses. Now on my calculator, when I do this calculation, I need to do the exponent first and then multiply by 4.6, and I get that the population is about 4.9 million. Let's do one last example because these are really not that bad. Again, I'll just tell you the words and you can just write down whatever I put on the board. So a factory purchased a 3D printer in 2010 for $3,000. The value of the printer depreciates at a rate of 7% a year. What is the value of the printer after 10 years? Round to the 100th place. Okay, so again, we're putting y equals and then our initial amount, which is 3,000. And then it says it's depreciating at a rate of 7%. So something is depreciating, that means it's going down in value. So I would subtract the 7%. And then it asks you for the value after 10 years. So I would put a 10 here. Then I simplify what I have in my parentheses as 0.93. And then following PEMDAS, I would do my exponents first and multiply. And I get that the printer is about $1,451.95. All right, good job, you guys. Nice start to chapter 6, and I look forward to seeing you soon.